Explainable AI. First of all, introduce myself. My name is Pedro Moreno. I work as a postdoc research fellow in Marvin-Gill's group. My research field is, as you can see, explainable AI. Okay, and how applying some techniques in order to make more friendly this machine learning, or make more explainable this machine learning algorithms or output to the, in this case, to the healthcare professional or even patient. So this is the outline of the talk, just to talk about the context of the explainable AI in healthcare. We will see some definitions and goals of the explainable AI. We will go a bit in detail into the explainable AI techniques, then see our experience, the different work that we are working in this field, and some conclusion. I won't stop very much here because, from the talk of Mark and Tunç, well, this is quite redundant, but only to make the emphasis in that the impact that artificial intelligence has in healthcare is quite big and quite potential. The data-driven health that the artificial intelligence bring into the field is quite powerful, but however, there's some barriers to overcome in order to be successful into adopt this technology into the real clinical routine. Here you can see different applications that Mark and Tunç has mentioned before. From the very beginning, when the artificial intelligence was coined as a concept, we had a quite simplistic algorithm and quite, let's say, transparent algorithm. You can see here in a regression in which we have different data points, collected data points, and we try to set a line in order to classify or to predict a certain disease or a certain outcomes. Then here we have a decision tree in which we can vary some set of rules after applying the decision trees. But nowadays, the task in which we use the artificial intelligence is becoming more complex, and we need more complex algorithms. In this case, for example, we have this is not for healthcare, but it's a face recognition application. And we need here a deep learning model, which is composed of different layers of neurons with a lot of connection between the neurons. So it makes more complex to understand why the model is making the decision that is. So if we move to the healthcare field, okay, when we are using the artificial intelligence in healthcare, eventually these algorithms are affecting the human lives, okay, by saying you are prone to have a disease, or you have this certain figure of having this risk disease, whatever. So not only the doctor, but also the patient demands a need of understanding the AI model, why the decision is being made. We can have different explanations depending on the model that we are using. For example, here, I don't know if you can see it, we have the probability of suffering a risk attack. And it can be, well, we have different features, okay, and a coefficient associated for each of the features. And if I have the exercise frequency would have a low influence in having, or better say, if I do low exercise, I have a high risk of suffering a heart attack. But depending on the other hand, if we use a very complex model, we see how the formula is getting more difficult. Okay, and the even explanation of this formula is not so easy as this one. In addition, the healthcare professional, when they are using this kind of model, they need more information than a simple binary prediction. In the case that we are using a classification model, they need more information about that the model says, okay, this patient is going to have a cancer or not. They need why the model is doing this, is making prediction or this information. And of course, we or the clinician need to avoid this non-justifiable decision, because it reverts on the accountability of the decision. So if the clinician trusts on the model and he said to a patient, okay, you have cancer, and then that patient has any kind of problem because of that classification, who is the responsible of this problem? Is the algorithm? Is the doctor? So that's why we need this kind of explanation, just to work on the accountability.
So when you say non-justifiable, you mean that it's not clearly visible, that's why?
Yeah, because it's a thing that I wanted to say in the conclusion. We are talking about decision support system. Okay, this system tries to support the decision of the clinician. It won't never, or it shouldn't substitute the clinician in that case. So this accountability is about it. So here, this is related with one of the previous slides. As you can see, there is a kind of trade-off between the accuracy of the models and the explainability of the models. So the more complex, the less explainable is. As you can see here, I don't know how familiar are you with the machine learning techniques, but here we can see that the deep learning is the less interpretable model, however, is the most accurate. On the other hand, we have the rule-based learning are the most explainable, but the less accurate. Anyway, there is this green zone represents the research area in which, the researcher and clinician as well can investigating how make more interpretable those best accurate model and make more accurate those most interpretable models. And when I say that this green area is for the researcher or data scientist, but as well to the clinician, there is here, as we are talking about the medical field, there should be a collaboration between these two kind of users in order to say, because, for example, in a certain disease or in a certain problem, it is not really needed to know why the model is getting the prediction. It's only needed to see the classification, but in other cases, they truly need the explanation of the prediction. So this explainable AI is quite recent research field. You can see here the trends, an exponential trends of studies, and together with the general explainability, explainable artificial intelligence field, we have the medical explainable artificial intelligence. In the literature, there are some definitions about explainability, about explainable AI. Okay, but I put this because it makes quite emphasis on the audience. Okay, because in the explainability, it's really crucial the audience, who is the listener, who is the people or the actor who is receiving the explanation, and what they will do with the explanation that they are being provided. So here we have the domain expert of the domain expert of the user of the model. In our case, it would be the clinician. So they need the explanation to trust on the model and then to apply the model in their discipline. Then we have the user affected by the model. Okay, in our case, it would be the patient. They need to understand why the model is giving such a decision, because in some way their life is going to be affected. We have the regulatory entities and also the public bodies, and all that they need this kind of explanation in order to bring the model into a clinical routine. Okay, and then ourselves, the data scientists, in order to advance the technology, to advance the state of the art of the different techniques. And of course, managers and executive board members who are the ones that are decision makers and put these systems into practice. Okay? The explainable AI has different goals, as you can see here in the slide. First, we have the trustworthiness, because the explainable AI is in the way to make the model trustworthy. Okay, because if a doctor understands the decision, they will trust the model. It is also revolves in the causality of the model by making or by showing the relationship between different variables that we are putting into the model and then the output. And with the explanation provided by the explainable AI techniques, we can validate causality information, or even have a first intuition about this relationship and how the features and how the variables influence on the final output. Then we have the transferability, which is a common characteristic of machine learning, especially in deep learning, because we can use an algorithm or a technique that has been used for a specific field to another field. Then the informativeness, which, as I said, this especially in the medical field, we are talking about decision support systems, and the explanation provided by the explainable AI models allows or facilitates this decision support for the clinicians, and as well to avoid different misconception pitfalls. Then we have the confidence, since when we are looking at the relationship between the features and the output, we can see that the model is robust. The model is not giving strange or giving wrong results. So by looking at this correspondence between the input and the output, given by the explainable AI, we can see. Then the fairness, which is well, at least to me, quite important, because in the sense that we are looking at which are the features more relevant for having a certain output. We can discover that, for example, some tricky features has a race, sex, ethnicity of the user. They are really important for the outcomes, and we can get rid of these features into the model and make them more fair. Then we have the accessibility, because as I said, by giving the explanation not only to the clinician but also to the patient, we are making the model more accessible, and even the technology or the concept of artificial intelligence more accessible to those kind of users. Then we have the interactivity, because in some ways this explainable AI allows the users to tweak or to interact with certain values of the features of the information that we are putting into the model, and see how the output varies depending on the information that we are putting in the input. And as well the privacy, okay, because again, related to the fairness, if we are seeing that one of the features that is important for the outputs is related to the privacy of the user, we can eliminate these features in order to not to fall in a privacy breach. Then, as you can see here, well, in the machine learning field, we have a transparent model or transparent algorithms, and then black box algorithm. Here is the transparent model. I don't know how familiar you are with this kind of information. We have the linear regression, in which we have different features, and we try to establish a line or a plane or a hyperplane, and to derive a formula in which we have a different coefficients associated with the feature. Okay. Then we have the decision trees, in which we can establish some kind of rules depending on the division. Okay, because in these nodes there is a condition that can be met or not, and then the flow of the decision goes in one way or another. Then we have the k nearest neighborhoods, in which the classification is made depending on the distance of each of the instance has depending on the clusters. And then the rule-based learners that Mark has talked before, and other one, for example, the generalized additive model and the Bayesian models. And then we have these post hoc explainability techniques that are mainly for those models that are really, really complex, and they are seen as a black box model in which we don't know what is happening inside because they are really, really complex. There are a lot of mathematical operation inside, and it's really difficult to have a clear view about what is happening inside. So we need some kind of ancillary techniques in order to establish a relation between the input and the output. Here we have a classification of these techniques. We have the local explanation in which we gather a small subset of the whole subset and try to explain why the model works in this small subset in order to expand or to justify the whole function into the whole data set. We have the feature relevant, in which we establish that certain features of the input data are more influencing to the output than others. Then the explanation by example, in which we take individual explanation and try to generalize the working of the model by explaining those examples. Then we have the text explanation, and in this case, we try to produce rules about the functioning of this black box model. Then the model simplification, that we use a surrogate model, more simplified model, in order to even combine with other, in order to make, or in order to explain the whole functioning of the more complex model. And then the visualization model, in which, well, we see how the instances are classified in the different output, and we can see why the model is reasoning to classify this instance into the different classes.
Yes.
Yeah, sure.
So the previous slide,
This one?
the previous one.
Yeah.
So you told us about all this linear regression, decision trees, neural networks, Bayesian, and so on. But you didn't mention deep learning. Is it because deep learning could be a mixture of all of them?
No. Deep learning is here. It's in the black box model.
Okay.
Let's
So
say that
you distinguish between deep learning because it's very difficult to explain it in comparison to the other ones.
Yeah, well, in fact, deep learning is called as this because as you can see in this slide, okay, this is a deep learning structure in which we have different layers and different neurons connected one with each other. So that's why they call deep, okay, because we have many layers. So depending on the model that we are using, there are different post hoc techniques, because this post hoc is when we apply the technique to an already developed model. Okay, so in this case, we have the ensemble trees, which are some techniques that use different decision trees, and then they combine the results of each individual trees to make a general prediction. So in this case, we have this feature relevance. By these techniques, assess the number of when they build the decision tree in each of the nodes, the number of each of the features is taken into account to produce the condition, okay, the condition result. And then we can see here that there can be some features that has appeared more times in these tree nodes than other, and you see the feature importance. Then we have other techniques as a line in which it can be set into the local explanation, because here it generates artificial data sets around one individual instance and apply an interpretable model, and then expand to the general model, and it's able to say for each of the features of the input data, what is the influence? It is able to quantify what is the influence of each of the features into the final results. Here, this visual explanation, we have the PDP, the partial dependence plot, and here we see a kind of a trend. We take one of the features of the data set, and we see how the probability, in this case, for having cancer, I don't know which kind of cancer, but cancer, we can see here, depending on the age or depending on the years of hormonal contraceptive, how the probability of having cancer can fall. Okay?
So you're basically saying the one on the left is basically a regression. You're extrapolating the use of a limited like data set. You're extrapolating it to.
Yeah, that's right. Yeah, it aggregates. It takes one of the instances, and then it generates an artificial subsets around that instance. And by applying interpretable models like a linear regression, for example, it creates, let's say, one rules about this only instance, and then it applies for every of the instance of the data sets. Then we have more visual explanation, but also combined with the feature relevance techniques here. This is one of the most used techniques in the literature, which is supply additive explanation. It goes as well for each of the instances of the data sets and see for that instance by applying a game coalition theory, the influence of each of the features in one instance, and then it aggregates, and it is able to give a general picture of the model by saying, okay, for each of the instances and for each of the values which are the most influential. In this case, we have the hormonal contraceptive here as the most influential, because this could be a quantification of the influence in the probability of having cancer. Okay. Then, depending on the value of the feature, we can see how influence is the feature, yes. And here we have a kind of individual explanation. We are taking one individual case, and we see for that particular case the influence that, in this case, this patient has, for example, the age. This patient is 42 years old, and in this case, this age is reducing the probability of having cancer. And another kind of technique is the feature permutation importance, in which we took the whole data set and we shift for one of the feature at a time. We shift all the model and we see how the model is behaving. So if we change, for example, the age values between all the instances, and we see that the error of the model or the accuracy of the model is increasing, that means that the age is important. Okay. So on the other hand, if we change in this case smoke, if we change the values in the data set and we see that the accuracy of the model doesn't change at all, that means that the feature is not important. Then going to the deep learning cases, in this case, convolutional neural network, which are used mostly for computer vision tasks. There are different kind of explainability techniques. Then here we have the mapping the relation between the output and the input space, and we see here imagine this is a model that classifies that in the picture there is a dog. So it is able to, by using this kind of heat map, which are the portion of the image that are more influencing to decide if the picture is a dog or not. And in this case, it is classifying a cat. So it remark in the image which are the part of the image which has more influence to make the classification. And here this breadcrumb is also similar. There is another way of there is another group of techniques to explain what is happening in the neural networks. This is about mapping the input and the output, and this is going into detail what is happening inside the neuron. So you can see here it is also classifying a dog, and you can see here how the information is treated at a neural level, at a channel level, in the communication between different neurons, and then at the layer level, where you can see here a kind of dog face. Okay. So talking about our experience, we have different work in the explainability field, trying to. All of the work that we have here is based on classification tasks, not in regression. And here we try to classify or to diagnose chronic kidney disease, and in which we have taken a public data set, and we apply this framework in which we carried out different steps of pre-processing the data before training the model. Here it is quite important the step of feature selection, because by applying different techniques we are able to get rid of some features that are not important for the model, and we have been able to gain, as you can see, an accuracy of 97% with only 3 features out of 24. So in this case we are also revolving or also increasing the interpretability by reducing the number of features that we finally put into the training step, and somehow it's more interpretable for the clinician to say, okay, I have only deal with 3 features instead of 20, 24 or 25.
Is this using deep learning?
No, this is using ensemble trees. Okay, these algorithms are only ensemble trees. It's decision trees, which is the simple one, right? And there's the random forest, extra forest, AdaBoost, and LGBoost are ensemble trees that use a decision tree. The problem with the deep learning is that you need a lot of data in order to train the model. Okay, for example, it is easy when you are dealing with images, because the images you transform the images into a 3 channels, R, B, and G, and into the pixels. So by dealing with images, with a collection of images, you can have a lot of data that are put into the deep learning. But as you hear, we are dealing with only, let's say, tabular data, okay, and it's not it's, let's say, a baseline data. We don't have a time series data. We have only used this kind of algorithm.
So you can't even use a regression.
Yeah, for sure. Yeah. We can use regression as well, but
we can't use time series.
Not time series. No, we can. No, at least if we don't have any, if we will have more, let's say, timestamps in the data, we could use time series, but not here. So here, as I said, we use different kind of explainability techniques by looking at the three features that we selected. Which one is the more important? So running out of time.
We need to be wrong.
Okay. So yeah, all the works that we have done has been using the techniques that I've used, and they are different in different fields, like fibromyalgia severity stage. We are trying to see if the psychological variables are more influential or are more important than the pain variables, that is usually assumed by the clinicians. Here, this is a word that we use, explainable AI as well to the prediction of hospitalization in an emergency department. And I'm going to finish here. This is as well a work that we have done in the trustworthy part, more in the co-design process, not only designing but also assessing this kind of algorithms in a clinical setting. Okay, in this case, we co-design an AI system aiming at a classifier skin lesion, and we work with a very multidisciplinary team with clinicians, but also with lawyers, also with ethics professional, in order to design, and as well in the other case to assess this trustworthy. And yeah, finally, this is a project that we are working now in Tampere University, in which we will assess the cardiovascular risk by using explainable AI. And yeah, that's it, my conclusion.